For this example, we're going to be given some information, and using probability rules from the previous section, we're going to form the distribution table for ourselves. So with this one, we're going to roll a 6-sided die and flip a coin. So the information they give us, if you roll a 6, you win you win $100. Got excited there. No, just $100. That's still great, but not 1,000. Okay. If you don't roll a 6, you get to roll again. And on that second time, if you get a 6 on the second time, you win $50. If not, you lose. So what I'm seeing here are 3 possibilities. We're going to at most roll a die 2 times. We get a 6 on the first try, we win $100. We don't, we get to roll again. If we get a 6 that time, we get $50. But if we don't get a 6 either time, then we just lose, which means if we lose, we're getting $0 is the idea there. Okay, so with that, let's go ahead and make our table. So we're going to have values for X, and we're going to have their corresponding probabilities. So something that helps with this question is create a probability distribution table for the amount you win. And that right there tells me what my random variables should represent. So X is going to represent the amount we win. So with that, that means we can win $100. We could win $50. We could win $0. And that sets up our random variable there. Now for the probability piece, that's a little tricky. So what I'm going to do is make a little note to myself underneath about what happens in each of these scenarios. So to get $100, we roll a 6 on the first try. In fact, I'm just going to actually leave that as roll a 6. That's all we have to do, is just take a die, roll a 6, and we get $100. For $50, we roll not a 6, then roll a 6. And then for $0, we roll not a 6, then not a 6 again. Okay, so for the first scenario, picking up a 6-sided die and rolling a 6 is going to be a probability of 1/6. 1 out of 6 chance that we do that. This next scenario, I wrote the fraction down below because Staplet wants decimal forms. So with this, I'm going to go ahead and grab a decimal, and we want to go to at least 4 decimal places to keep our accuracy here. So I'm going to go 0.1667 for 1/6. Okay, this next scenario, rolling not a 6 and then rolling a 6. This is our sequence of events, and that's where we multiply probabilities. So we want to see the probability of one thing happening and then another. So I want the probability of rolling not a 6. Well, that has a 5 out of 6 chance of occurring. And then that's where we multiply, rolling a 6, which has a 1 out of 6 chance of occurring. So this has a 5 out of 36 chance if we multiply those together. And just put it in a calculator because we just want that decimal, 0.1389. And then what we have left over is rolling not a 6, which has a 5 out of 6 chance of occurring. And then we multiply with rolling not a 6 again, which also has a 5 out of 6 chance. So that'll be 25 out of 36 if we multiply those, or 0.6944. And then whenever I do these scenarios where I've created the table myself, check that the probabilities add up to 1. And this is a case where we rounded a bit, so let's see if we get any kind of decimal left over. 4. Nope, perfectly 1. We're all good there. Begin with rounding to 4 decimal places. If you end up with 0.9999, that's fine. If you end up with 1.0001, that's fine too. But anything else would say something went wrong with the probabilities. Okay, so now we have our table. This is really all we need for our table right here, but there was some side work involved to find those probabilities and organize it. Okay, let's go to Staplet with this one. So, finding expected value, let's go Staplet, open that up, discrete random variables. This is a case where we have 3 outcomes, so we have a value of 100, 50, and 0, and then our probabilities 0.1667, 0.1389, and a 0.6944. And let's go ahead and begin analysis. And we have a mean of 23.615 and a standard deviation of 38.1652. So let's go. Expected value. The exact value is 23.615. And then standard deviation, exact value is 38.1652. So we'll always write down the exact values before we make our sentence because we want to show that we've found the exact values. This is what they calculated to. And then from there we can make our sentence. And I'm going to go ahead and make a sentence together for these 2 pieces. So the expected winnings is about $23.62, and on average this will deviate by about $38.17. Now, this is a case that can occur and might feel a little strange where the deviation is larger than the expected value. So if we think about what this means, we expect about $24, and on average that can change by about $38. That's going to land us in the negative region. Why that's happening, like if I look at this, I'm like, ooh, I'm not sure about that. How could I double check my work without calculating things by hand? If you go back to the table, this is going to occur when 0 has a high likelihood of occurring. When we go into that negative region, so if we take that like $23.62, subtract away 38.17 and end up at a negative, that's just kind of emphasizing that 0 had a high likelihood of occurring. So those 2 pieces typically line up, that we expected very small numbers, and that kind of led to our larger deviation that would throw us into negatives. So just in case that wasn't sitting right with you, that's how we could think of that. Should you play this game if it costs $25? Why or why not? So what we just found is if we play this game, sorry, I did not want to cross that out. I wanted to highlight it. So when we play this game, in the long run, we expect to win about $23.62. So an issue here is they want to charge us above the expected winnings. So that would not be good for us. We'd be paying more than we expect to leave with. So with this, I would say no. The expected winnings are lower than the cost to play. So with this scenario, something that we can think about is profit and loss. So with business mathematics, we can think of profit is equal to revenue minus cost. So revenue is the money that we make, and the profit is kind of this difference of how much we're making when we take out those costs. So for this case, what we would be thinking of this as is taking those expected winnings, that expected revenue of 23.62, and then taking out this cost to play of $25. And if we calculate that, that'll be a negative 1.38. And what that's telling me is that we have an expected loss of $1.38 in the long run for each time we play. So with that, this would be considered an unfair game. It's unfair because it's rigged for the house to be making money off of you, which is how a lot of games in the real world work. And that's what I kind of wanted to emphasize with this example here, is that they have these expected values, they have these expected winnings for a player, and with that, they can choose a cost that seems like it would be good. Like, if I approached this game and they said, hey, you can win $100, $50, but you might end up with $0, you want to play, or you want to pay $25 to play, I might say yes, just looking at, ooh, okay, I would make $75 in this case, I would make $25 in this case. All right, but I might lose $0. Without knowing the probabilities, $25 might make me inclined to play. Maybe even $30 would make me inclined. If they asked me to pay $50, I wouldn't go for that, because either I would break even, lose $50, or maybe win $50. That doesn't seem so great. But choosing $25 was kind of strategic in that it sounds like a pretty good price to pay for this game. But then going through the calculations with the probability, we could see, ooh, but really we expect to make less than that. So say the house suddenly decided to charge $20 to play. That would be good for us. That would then be considered a fair game, because we would be expected to make money off of it as the players, and the house wouldn't be making money off of us. Doesn't sound so great for them, but that's part of it. So with these, we can think of expected value and comparing for a cost in order to see if it's an unfair game or not. And then with that, we can see what are the expected profits or losses based on the difference between those two values. So like I was saying, maybe I would even play this game for $30. So with that, I would have an expected loss of $6.38. Well, that goes to the house. So that might be good for the company running this game. They're like, ooh, okay, instead of making only $1.38 off of each person playing, we could be making $6.38 off of each person playing. And maybe that 30 wouldn't be too suspect. But like I was saying, if they suddenly made the cost 50, not as many people are going to play. So maybe that would bump up that like profit of theirs, but if not as many people play, it might not pan out for them. So there's this kind of sneaky cost to play that's this nice balance of working to make them money. So what cost to play would make this a fair game? So anything below, actually, sorry, to make it fair. That's my bad. To make this a fair game, the cost and expected value should be exactly the same. Because as we go below, that becomes unfair for the people running the game. Sorry about that. I stumbled on that a bit. But the cost to play, if it's exactly the expected winnings, then if that balances out, there's no profit, no loss. It would just be a fair game.